Good evening, all. In this session, we would like to see some of the definitions like Ohm's law, Kirchhoff's laws, and some of the circuit reduction techniques. Then Ohm's law. It states that provided at constant temperature, amount of current flowing in the conductor is directly proportional to the potential difference across the terminals. So I is directly proportional to V. If you remove this proportionality constant, so respective constant will appear in the expression V becomes I into R. Now you could able to see here Ohm's law triangle. V equal to I into R, I equal to V by R equal to V by I. This everything, the phenomena is being observed by the Ohm. That is the reason whatever the value of the constant R here, the resistance is being measured on his name. It has a linear properties since current is directly proportional to the voltage. If the one thing is getting increasing, other thing is also getting increasing about like a ramp signal. You can able to see the characteristic curve here, graph between current and voltage with respect to the applied resistance. Some of the limitations of the Ohm's law, like it cannot be applied to the unilateral circuits, and it does not hold good for non-metallic conductors such as like silicon carbide. And this law is not applicable for the nonlinear elements. And this law not obeyed by the vacuum tubes, discharge tubes, semiconductors, and electrolytes. Some of the applications of the Ohm's law, if you're able to see here, conventional domestic fan regulator is one of the very common device where the current through the fan gets regulated by controlling the resistance of the regulator circuit. Other application we can able to see in the electric heater, then speed control of DC motor via armature control methods. And in electronic circuits, there are many purposes where intentional voltage drop is required to supply a specific voltage across different electronic elements. There also, it is being applied by the Ohm's law only. In mainly DC ammeter and other measuring instruments, shunt is used to divert current. Here also Ohm's law is used. And some of the example with a numerical you could able to see here. An electrical iron carrying 2 amps at 120 volt. Find the resistance of the device. By Ohm's law, you need to find the resistance here R equal to V by I. Given V equal to 120, I equal to 2 amps. R equal to 120 by 2, 60 ohms. Another numerical also you could able to see here. A small circuit has been given where RMS supply current is 115 volts and resistance is being about 100. So resistance is given. You need to find out through that resistance some sort of power is observed about. It is about 100 watt bulb. So resistive load is being connected to the supply 115 volts. So P equal to either we can go with V into I or I square into R or V square by R. R equal to from these any of the expressions you can calculate. So V square by P based on the given parameters you can choose the option. So voltage is being given and the power is being given to us. R equal to V square by P. V is 115. R equal to you need to find. So it will be about 132.25 ohms. Some of the network analysis methods and the circuit reduction techniques we will able to see here. In the circuit reduction techniques, we have the following techniques like series connection, parallel connection, source transformation, star delta, voltage division rule, current division rule, KCL, KVL, nodal analysis, mesh analysis, and some of the network theorems. Series connection, if we want to go with first with the passive element R, so in the case of series, when n number of R are connected in series, equivalent resistance will be sum of all the individual resistors. So R equivalent becomes R1 plus R2 up to Rn. Similarly, if only three resistors are connected in series, R equivalent becomes R1 plus R2 plus R3. Now here some sort of numerical has been given with respect to some DC battery applied through R1, R2, R3. Then if I want to find the drops across the each resistor is across R1 it is V1, across R2 it is V2, across R3 it is V3. So net voltage supplied should become equal to sum of the all individual drops about. V becomes I into R1 plus I into R3, I into R3. Then finally V becomes I into R equivalent, where R equivalent we can represent as R1 plus R2 plus R3 ohm. Then similarly, another parameter, inductor. Resistor and inductor parameters, they both analogous to each other in the series, either in series or in parallel. So here two inductors are connected in series. Then L equivalent will be same as to that of the resistors. So individual components will be added together. L equivalent becomes L1 plus L2. And whereas coming to the capacitor, it is reverse. When two capacitors are connected in series, then the equivalent capacitance, if we want to find out, so 1 by C equivalent becomes sum of the reciprocals of the individual components, 1 by C1 plus 1 by C2. Then C equivalent becomes finding of the LCM. So C1, C2 by C1 plus C2. Then parallel connection with n number of resistors. Here, three resistors are connected in parallel with a supply battery V. Then R equivalent will be same as to that of the capacitor in series how we have seen. So 1 by R equivalent becomes 1 by R1 plus 1 by R2 plus 1 by R3. As I have told earlier, inductor and resistor, the properties are analogous to each other. So similarly, in the case of inductor also connected in parallel means if two inductors are connected in parallel, then 1 by L equivalence will be equal to sum of the reciprocals of those two individual components. 1 by L1 plus 1 by L2. Then capacitor in parallel. So capacitor parameters, coming to capacitor parameters, the properties are vice versa. They are reciprocal to that of the resistor and inductor, reverse to that of the resistor and inductor. So if two capacitors are connected in parallel, C1, C2, then C equivalence will become adding of the both, just directly adding of the both, sum of the individual components, C1 plus C2. So summary has been mentioned here, just a tabular column with respect to capacitor, resistor, inductor, series and parallel. In the case of series capacitor, two capacitors connected in series means 1 by C equivalent becomes 1 by C1 plus 1 by C2. In the case of resistor, R becomes with two resistors, R equivalent equal to R1 plus R2. In the case of inductor also, L equivalent becomes with two inductors, L1 plus L2. In the case of parallel also, if you see with respect to the capacitor, C equivalent becomes C1 plus C2. Then reciprocal of R equivalence becomes 1 by R1 plus 1 by R2. In the case of inductor, 1 by L equivalence becomes 1 by L1 plus 1 by L2. Then Kirchhoff's laws. Kirchhoff's current law, KCL. It states that the algebraic sum of currents at a particular entering at a particular node or junction, or algebraic sum of currents meeting at a particular node or junction equal to 0. Summation I will become equal to 0. With respect to the node or a junction, if you want to see the representation or denotation of current, if current is entering into the node, the notation will be given as a positive sign. If the current is moving out from the node, notation will be given as a negative sign. So entering current, we can also call it as a incoming current with positive sign. Moving out current or outgoing current, we will also call as a, we will represent outgoing current and we will represent with a notation of a negative sign. Here some n number of currents are meeting at a junction. Some are entering into the junction or some are moving out from the junction. So based on the notation, if you could able to observe here, I1 is entering, I2 entering, I3 entering, I4 and I5 are moving about. So net current here will be equal to I1, I2, I3 will be represented with a positive notation, plus I1, plus I2, plus I3, and I4, I5 will be represented with negative notations. I1 plus I2 plus I3 minus I4 minus I5 equal to 0. So then you represent the final expression like I1 plus I2 plus I3 will become equal to I4 plus I5. Then some of the numericals has been mentioned here. Similarly, Kirchhoff's voltage law. So it states that the algebraic sum of voltages in a closed loop equal to 0. In a closed loop equal to 0, summation V equal to 0. Here some sort of resistors are connected in series. So with the provision of some DC supply, then whatever we have provided the DC supply should become equal to all the drops across the individual components in the circuit. Or this algebraic sum of supply voltage and all the drops, addition of all the drops should become equal to 0. So V equal to, since I have taken here 3 resistors, across 3 resistors, 3 drops will be there. So algebraic sum of voltages in this closed circuit will become as V equal to V1 plus V2 plus V3 or V minus V1 minus V2 minus V3 equal to 0. You could able to see some resistance parameters has been mentioned here. R1 10 ohm, R2 20, R3 30. Potential DC battery supply I have given here 12 volts above, and where amount of the current flowing in this particular series circuit is about 0.2 amps above. Then by KVL, V equal to 12 volts will become equal to R1 into I in plus R2 into I plus R3 into I. Otherwise, V minus IR1 minus IR2 minus IR3. So with respect to the voltage at resistor R1 or the voltage drop at R1 becomes, so I into R1, V1 equal to I is 0.2 amp, R1 is 10 ohm. So drop will be 2 volts across the resistor 1. Similarly, across the resistor 2, R220, current flowing in the series circuit remains same, 0.2 amps only. So 0.2 into 20 ohm, 4 volts. And here across resistor 3, opposition resistance is 30 ohm. Current is same only 0.2 amps. So 30 into 0.2, 6 volt. So you add all these three drops, 2 plus 4 plus 6, 12, equal to the what we have applied about. Or if I add all these drops with respect to the provided supply, so it should become equal to 0. 12 minus 2 minus 4 minus 6 equal to 0. Then some of the applications of the Kirchhoff's laws can be used to determine the values of the unknown values, like current, voltage, and also it is used in the node and mesh analysis for finding of the current and voltage parameters. And it is also used in torch. These laws are prominent in every single trace that we create on PCB. And some of the limitations of the KCL you could able to see based on some assumption that there is no fluctuating magnetic field in the closed loop, and electric field and EMF could be induced, which causes the Kirchhoff's loop rule to break in presence of the variable magnetic field. And also KCL is valid only if the total electric change is constant in the circuit. And this law not good for high frequency circuits. Next, if you want to see here, we can have a glance source transformation. So here we could able to see two types of the source transformations. Current source to voltage source transformation and voltage source to current source transformation. We shall see in the next slot. Thank you.